Got it. Okay, so we did not finish example one. We were reviewing continuity at a single point. And for the most part, we did the continuity part, but just to extra review the end behaviors. So you just got to make sure you're using the right piece, depending on which x value we're approaching. If we're going to a negative infinity is to the left of -2, maybe, yes? Yeah, so we would be using this piece. So again, if you want to write it so that it's more helpful in front of you, the limit as x goes to -infinity, and then you could bring that part of f into here, right? And now, let's see, the top stays a 1, the bottom gets really, really big. That means the magnitude of the ratios are approaching 0. Yeah, and this one approaches from underneath, because when you plug in a negative value, you get +1 over negative. So whatever, you know, we know what the graph looks like, 1 over x plus 3. Hopefully we do. And then the other one, the limit as x goes to infinity. If you want to write out the piece that it's 8 root x, so 8 root x, and you can use direct substitution here, right? But don't write it. Don't do this, right? Otherwise, it's a heart attack waiting to happen. Not for me, but you know, somebody else. The square root of infinity is infinity, right? And what's infinity times 8? Infinity, yeah, infinity, bigger infinity. So infinity is the better answer, but DNE is a safe answer, right? So, hey, because the limit goes to infinity, does that mean there's a vertical asymptote there? No, because this is end behavior, right? That's only if it happens as you're approaching a specific value of x. So here's what that graph looks like. It goes up. It goes up pretty slowly, faster than the log functions, but not very fast, okay? So there's the review of continuity at a point, right? Road, bridge, road. Road in, bridge, road out. So if you're still doing it like horizontally, like road, bridge, road, and writing left to right, try to flip it 90 degrees and do road, bridge, road, okay? If you want to put equal signs, you can. What I mean by equal signs, like where would you put them? I guess you'd put it here, you know, in here, there, and here, if you want. You know, if it feels weird not having equal signs, I get it. Okay, like that. All right, now we're ready for continuity on an interval. Wow. So here we go. A function f is said to be continuous on an interval. Call it I for interval. If and only if, that means it's a definition. It's a postulate. It works both ways. If and only if the function is continuous at every single point in the interval. Okay, well, that makes sense. So when we talk about an interval, let's just look at an interval. It could be an interval like this. This would be an interval, odd and ordered pair. And if you're not quite sure, you can put x epsilon. That kind of means, oh, those are both x values. That would be an open interval, right? Or we can have something like this. That would be a closed interval. But they don't have to be all or nothing. You can have something like this, which would be half open. And then you can have something like this, which would also be half open, right? Or half closed if you're a pessimist, I guess. So those are the types of intervals. You can also write those with inequalities, believe it or not. So like this one here would also be the same as a less than or equal to x less than b. So you could actually define an interval with an inequality. But we're talking about real numbers here, the real number line. So it says a function is now continuous on an interval if it's continuous at every point on the interval. Well, how many points are there between any 2 points on the number line? Infinitely many, many. Infinitely many, many, many. Yeah, in fact, it's actually true that there are just as many numbers on the number line, and this might blow your mind before lunch here, but there are just as many numbers on the number line between 0 and 1 as there are on the entire number line. And you might think, no, hombre, there's infinitely many more on the entire number line because I have infinitely many segments, like 0 to 1, infinitely many, 1 to 2, infinitely many, but no, it's the same size of infinity. There's different sizes of infinity, believe it or not. And those are the exact same size of infinity. They're non-countable, infinitely large. It's the same. So yeah, So do you think then that we're going to be testing for continuity on an interval by using the three-step definition of continuity at a point, at each and every point on the interval? Probably not, because think about it. If there's 3 steps we have to do for each point, and there's infinitely many points, what's infinity times 3? Infinity. That would be infinitely many steps we'd have to write. So that's not feasible or possible. So that's not obviously how we're going to do it. I'll show you how we're going to do it. All right, let's go ahead and specify then what it means to be continuous on an open interval, which will kind of lead into what it means to be continuous on the closed interval. A function now is said to be continuous on a closed interval if and only if it's continuous at every point in the open interval. Well, that's almost what the previous one said, right? But the previous one was on any interval, okay? So how are we going to test that? Well, here's how we're going to test it. We're going to test it either with our knowledge of particular types of functions, like polynomials. We know, for instance, polynomials are continuous for all real numbers. So pick any 2 x values that are different and look at the interval between them. A polynomial is going to be continuous on that interval because we know that's true about polynomials. What are some other functions that we know are continuous, let's say, for all real numbers besides polynomials? Polynomials, just to remind you, are nice integers, nice positive integer exponents, like x cubed, x squared, x to the 5th, not x to the 1/2. Exponential functions are continuous for all real numbers. Good. E to the x, 2 to the x, even 1/2 to the x. Are there any trig functions that are continuous for all real numbers? Sine and cosine are the only 2 that are continuous for all real numbers. Yeah. So if you see one of those graphs, you're like, oh, continuous on the closed interval for sure, for sure. Now, there are some other functions that are continuous over their entire domains. That means where they're defined, they're continuous. And that would be the other trig functions, the natural log of x. Arctangent's continuous for all real numbers. Yes. So that should have gone on the previous list. But also over its domain, which is all real numbers. The square root of x, like we saw on the right end behavior. It's not domain of all real numbers, but it is continuous over its domain. All right. Now, if it's not a function whose equation we memorized, the way that we're going to tell is, let's just write this out. We can tell by, number 1, we recognize a known function. Or I guess I should say we recognize a known continuous function. And you can put some examples there if you want, like arctangent of x, sine of x, polynomials. But if it's not something we recognize, and we can either generate a graph of it to see it by analyzing where it's not continuous, or we are given the graph, we're going to call method 2 using our peepers. Okay, that's the official term. We're going to use our peepers. We're literally going to look at the graph and say, is it continuous from left to right? Much like we did up here when we opened this section, right? Look at this. I don't know what the equation is of that right there, but assuming that those arrows mean it keeps on keeping on, this graph I would say is continuous on any open interval, right? It's continuous for all real numbers on any interval, right? Pick this as A, pick this as B. Yep, it's going to be continuous at all points in between, okay? Which means that if there is supposed to be like a hole in there, you don't want to draw things to scale, right? Like if there is like a hole, you don't want to try and draw that purple graph as close to each other on either side as possible without touching, right? Because really, how thick is a point? Infinitely small. So if you try to draw that hole to scale, you know, it's going to be, I think you think that's continuous. No, sir, there's a hole there. Can't you see it? No, I cannot. I cannot see it, right? So that's why if there were to be a hole, we would accentuate it with a giant open circle. All right, now, open interval, we're going to check with our peepers. We're going to look at it. Now let's step up to the largest interval something can be continuous on, assuming we have endpoints. It could be all real numbers. A closed interval, okay? Because that's the endpoints. A function f is said to be continuous on a closed interval beefy bracket A to B, close beefy bracket, if, number one, it meets the previous requirements, it's continuous on the open interval. You either recognize the function or you look with your peepers and you're like, ooh, smooth. And then there's some analysis that we have to do. We have to look at the endpoints separately, okay? If the limit from the right side only of A is equal to the function value, and the limit as you approach B from the left side is equal to the function value, then it's continuous at the two endpoints. Now, that is an exception right there. Let's just draw a little graph here that would be continuous on the closed interval. There's A, there's B. So look strictly in between A and B with your peepers, right? I spy a continuous function on the open interval, check. Now, what do those other two pieces mean? If I approach A, bless you, which is the left endpoint of my interval, from the right-hand side only, and it equals the function value, then the left endpoint can be included. And similarly, if I approach the right endpoint from the one side, the left side of it, and it equals the function value, then I can include the right endpoint. Now, that's an exception because when we talk about the endpoints, we're talking about points, right? And we just had a three-step definition for continuity at a point, and it had to be road, bridge, road. Well, here we don't have road, bridge, road, do we? If you look at A, there's no road coming in from the left. So it would automatically be excluded from being continuous at that point, even though it has a bridge and a road going out. What if nothing lived to the left? You wouldn't need a road coming in from nowhere, right? What if this was a cul-de-sac? And you're like, we like it down here. It's one way in, one way out. Same thing on the right endpoint. There's no road going out. So rather than exclude it, trying to make it an intuitive idea that, okay, if there's nothing over here or nothing over here, we shouldn't automatically exclude the endpoints just because there's nothing there. So, okay, let's say, well, if then at least the function value is tied to the road on both sides, then we can say it's continuous at those endpoints of the closed interval. And that's why we can say something like this, you know, you can say that the function square root of x, which we just saw in the warm-up, we can say that this function y is continuous for all x greater than or equal to 0. Or you could say on the interval from 0 bracket to infinity. Now, if you state the domain as all x greater than or equal to 0, and that's listed, bless you, and it's listed somewhere, then you could say it's continuous over its domain. But without the exception to the rule, the three-step definition, we would not be able to include 0, would we? Because there's no road coming in from the left. If you look at 0, road, bridge, road. Road, bridge, road. I got bridge, road, but I don't have road. Sorry, you can't. No, you can. You certainly can. Because intuitively, it looks good. Right? Would you agree? We basically have, like, this is a rope, and we've tied off the knot at the end, right? So that we don't get frayed knot, right? Now, speaking of frayed knot, what if this were a piecewise function and that were an open circle, and we still had the function defined at 0? Would that function be continuous now for all x greater than or equal to 0? No, it wouldn't. Okay, frayed knot, you might say, because now the knot is getting frayed. There's no knot there keeping it from fraying. So it can be defined but not continuous. It's only when they're the same. So we have made the exception for an endpoint. All right, and you can consider those independently, but a function is only to be considered continuous on the closed interval if in between A and B, no discontinuities, peepers, or you just understand. And at the endpoints, the roads go into the bridges. That's an easy way to think about it. Now, this is a super important idea because we're about to learn some theorems, not just the squeeze theorem or the sandwich theorem. We're going to learn the IVT, the EVT, and then a couple of MVTs. And those theorems that we're going to learn only work if the function is continuous on a closed interval. So Continuous functions on closed intervals, very, very important types of functions because we can draw certain conclusions from them. All right. All right. So let's look at example 2. We have a graph of f of x. So we're starting with our peepers here. Determine the largest intervals on the closed interval from 0 to 3 for which the function f is continuous. Okay. So we can't say that this function is continuous for all real numbers. Can't even say this function is continuous for all numbers between 1 and 3. But we can say this. You could say that f is continuous for x epsilon. I like to do it when we have intervals. Now, let's just go from left to right, and we'll list the largest possible intervals we can have. So looking at the left endpoint of 0, can I include, well, let's look at the open interval. It looks like the largest open interval that I can start with is 0 to 1. Would you agree? Because after 1, there's a hole there. Now, can I include 0 with the bracket is the question. Yeah, you can consider endpoints individually. Yes, the road goes into the dot, so that's good. Can I include 1 in it? No, I can't. So that would be a half open interval, okay? Then I'm going to put union, and then I go to the next open interval, which looks like it spans from 1 to 2. And then I do the same thing. Now I consider the endpoints. Can I include 1 as a left endpoint? No, it still goes into an open circle. Can I include 2 as a right endpoint? Yes, I can. Bracket. Union. I pick back up. The next open interval is from 2 to 3. Can I include 2 now as a left endpoint? No. Okay, I cannot. It's open up there. So parenthesis, and can I include 3 as a right endpoint? Yes. Okay, and that's it. That would be the largest listed interval over which this function from 0 to 3 is continuous. So notice that an x value can be included on one interval and simultaneously not included on the next interval, okay, when you have a jump discontinuity like that. Okay, so that's why it's important to kind of get in the habit of just looking at open intervals in between open intervals, and then yes or no on the endpoints. Okay, there you go. That's it. That's it for that one. Number 3, go ahead and take a second to do this on your own, part A. On the interval from negative infinity to infinity, and we can assume that those green arrows mean that graphis interruptus continues, in the same manner eternally forever, okay? Go ahead and write the largest intervals just like we did for this function. It's going to take a little bit longer. I'm going to do the same thing, and we'll just compare answers. Okay, you might already be done. I think that's it. Yeah, that's more than you're ever going to be asked to do. But if you understand that right there, then you've got the peeper method down. You just hop on the graph and move from left to right until you hit a discontinuity. And when you hit a discontinuity, then you just ask yourself, am I ending at a point? If so, include it. If not, don't include it. And then you start on the next bit of the road. Can I include it or not? Mm-hmm. So 6, x equals 6 is the only jump location there where it was included on one point part, but not the other. So, okay. So understanding how to do that then will help you then with these types of questions. And these are the types of questions that can show up really easily as a multiple choice question. In fact, if you work the exam for 1.5, I think the very first question was something like this. All right, so find the largest value of b, assuming b is just a real number, where this function here is continuous on the half open interval from 5 up to that b value inclusive, but not from 5 to b plus 1 inclusive. So that's one. And it says to find the largest value of b. There might be more than one that work, but I want to find the biggest one. So for something like this, we're starting at 5. So here's 5. So I'm cruising just to the left of 5, and thank goodness there's a parenthesis around 5 because there's a vertical asymptote. So as a left endpoint, I wouldn't be able to include it. And if I keep cruising all the way up until 6, I would be able to include 6 as a right endpoint. So I know that when b is equal to 6, I think it might work. Let's check. Okay. Is this continuous from 5 to 6? Yes, right? So that's the first part. I need that to be true. But then I need it to fail on the next interval. So now, what about from 5 to 6 plus 1? Inclusive. Well, that would be 5 to 7. And I want that to fail. Does that in fact fail? Yeah, it fails because now it fails successfully, we should say, right? We want it to fail. It says, but not in this interval. So this is successfully not continuous on that half open interval because it's not continuous on the open interval, right? It spans the jump. So we know that b equals 6 works. But is there a larger value that works for this but not for that? I don't think so, right? Because as soon as I go anything past 6, I'm spanning the jump, and now I'm not going to meet this first requirement, right? I'm not going to meet the first requirement. So 6 would be the answer to that if this were a multiple choice question. It is continuous from 5 to 6 inclusive, but not from 5 to 7 inclusive, and there's no other value. Now the follow-up to here is to find all the values of b that work. Now when we list all the values of b that work, we could list the solution set as an interval. But that's going to get kind of confusing because we're looking at intervals of a graph and then a solution set interval. So I'm going to write this solution set as an inequality. I know that 6 is the largest. So I know that b can be 6 and have those two criteria met. And can it be smaller? What if, would 5.5 work? Yeah, the condition is I would need it to be continuous from 5 to 5.5, and it is. And then I would need it to fail from 5 to 6.5. Does that fail? Yes, it fails successfully, again, because, again, it takes me past the jump. So this fails because it's not continuous. So, yeah, B could be 5.5. 6 is bigger, which is why it's the biggest. So I guess now we're looking for a lower bound. Is it 0? 5. Yeah, it's 5. Now, can B actually be 5? No. Try it out. If B were 5, you'd be looking at the interval from 5 to 5. Is that an interval at all? No, that doesn't span anything. So, yeah. So here we go. These are all the values of B that make these interval criteria work, okay? Now, again, notice, not to confuse anyone, but after the fact, you could write the solution set for B as an interval. Two different contexts though, right? One's a solution set interval, talking about a graph and looking from left to right on its x-axis, okay? So that's why I listed it as an inequality. All right, so now that you kind of have the idea there, go ahead and do part C, D, and E on your own, all right? And then we'll talk about it. C, D, and E on your own. Okay, it looks like y'all got C. We want the smallest value of A so that it's continuous on the largest interval from A non-inclusive to 10 non-inclusive. So in this case, we have our final destination, our endpoint on the right established, and it's right here. So now if I want the largest interval, I'll backtrack as far as I can, which means I can backtrack all the way to 8, right? Now, because this is open on both ends, then A equaling 8 is going to give me the largest open interval from the number to 10, right? A can't be smaller than 8 because then that spans the jump, or it spans the hole in this case, or is it, yeah, it spans the hole, and it won't be continuous on the open interval anymore. And thank goodness both of those were open parentheses, right? Because neither one of those graphs goes into the knot at the end or the bridge at the end. Okay, but are there other values of 8 that will make that interval continuous? Yeah, is this a true statement? That graph is continuous from 9 to 10? Yeah, it's continuous from 9 to 10 on the open interval, sure, yeah. How about from 9.9 to 10? Yeah, how about from 8.1 to 10? Yeah, so all of the values that make it work, we know then that 8 is the smallest or largest. Smallest. Largest? Smallest. Okay, so it goes on this end. And can A be 8? Yes, right? And that's why it's less than or equal to. But what is the absolute largest that it could be and not be? 10. Okay, so again, don't get confused. That is a solution set. A, the left endpoint of that open interval from A to 10, that value can be anything from 8 inclusive to 10 non-inclusive, right? Sometimes people look at this and they get confused and like, sir, you put an equal sign here and it's supposed to be open on both ends, right? And I get that, right? Yeah, this interval is open on both ends, and that's why this one has to be equal, because 8 works when you plug it in over there, right? Does that make sense? So not only did I leave that as an interval and write this as inequality, I wrote them far away from each other, right? X interval of the graph, solution set for our variable, okay? Different things. And then what's the smallest k value? So the function will be continuous from k to infinity. So we can kind of start working backwards from infinity. I'll start over here around 20. I don't want to go all the way to infinity, just come back, silly. And then I start working back, and looks like I hit a discontinuity right there at 11. So to make the largest interval, I guess k would equal 11, right? That makes it the largest, because this would be continuous from 11 to infinity. So that would give us the largest interval. Are there other k values that work, though? Yeah, that one's pretty easy. You could choose anything bigger than 11, right? Any value 11 or bigger. So it didn't ask us for this, but just to kind of keep the same thing, all values 11 or bigger will make that interval continuous from that number non-inclusive to infinity, obviously non-inclusive. But this one gives us the largest interval, 11 itself. All right, and then it says to find the small IVK so it's continuous. Well, what's the difference between those two intervals? They look the same. One's inclusive, one's non-inclusive, right? Now I want to be able to include the left endpoint. Can k still be 11? No, it can't be 11, right? Because I can't include 11 as a left endpoint. It's not filled in. So I guess if I want to include it, it would have to be the first number after 11. What's the first real number after 11? It doesn't even exist, believe it or not. Because as soon as you think you found it, I'm going to zoom in. And I'm going to get between that number and 11. That's what I do. I'm going to keep y'all apart, right? I don't want anything to start between y'all. Zoom in and get between y'all. Yeah, there's no first real number past any other number. We know numbers exist, but only by the well-ordering principle, we call it. So in this case, we would say there's no such k value. Or k is DNE. K is does not exist is, sir, ever. Yeah, no such k value. And that might be an answer. I didn't want to like give you a hint in the question, like find the smallest value of k, comma, if it exists, you know, comma. But that's probably what College Board would say. Okay. All right. So far, so good? Been easy? Not bad. Not bad. All right. So again, this is because the theorems that we're going to talk about depend on continuity so much. This is a non-exhaustive list of functions that are continuous over their domains. Polynomials, rational functions even. Rational functions, they can have holes and they can have vertical asymptotes, but those would not be in the domain. So any interval that is in the domain, that spans a domain, is going to be continuous, okay? Now, if you look at the ones with the asterisks, those are the ones that are continuous for all real numbers. So pick any two values on those, and it's going to be continuous on the closed interval. The others maybe not so much on the closed interval, right? But continuous on their domains. So we already talked about those. I think the same ones: polynomials, sine and cosine, exponential functions, and of course, Mendeley.
Oh, arctangent.
Arctangent. Yeah, arctangent. Okay. All right. So let's go ahead and do example 4, which is kind of getting into what's going to end up being kind of a little bit of preliminary work for the theorem. Find the intervals, or give the intervals for which the following functions are continuous by finding their domains. Okay. Well, why is that going to work? If we have two continuous functions, like anything from the list up there, and we combine them in new ways to make new functions, adding, subtracting them, multiplying them, dividing them, composing them even. If you combine two or more continuous functions in any of those fashions, you will get another function that it happens to be also continuous over its domain. The domain might change. Like if we divide two functions, we might divide by 0 now, but that would not be in the domain. So that's really important. If you combine two or more continuous functions, add, subtract, multiply, divide, compose, you're going to get another function, a brand new function that is also continuous over its domain. So look at example 4 now. If I want to find where this function is continuous, all I got to do is find its domain. Why? Because it's composed of x squared on the inside, which is a polynomial, and sine on the outside. So if I can find the domain of h, that will also tell me where this function is continuous. All right, so now that we've reduced the continuity question to a domain question, domain questions are a little bit easy to answer. Because remember, for domains, unless it's a piecewise function, or even one in disguise, like Senor Salta, we're really trying to avoid 3 things, right? Number 1, division by 0. Division by 0 is a no-no. So if you ever see, you know, a denominator with a variable in it, or in the numerator with a negative exponent in a variable, any value that gives you a 0 is going to be not in the domain, right? What else are we trying to avoid? We can't take square roots of negatives at all, right? Can't take square roots of negatives, or 4th roots of negatives, or 6th roots of negatives, so on and so forth. So if you ever see a radical or a fractional exponent with a variable in it, that might restrict the domain if it's to the 1/4 power. Okay. Now odd radicals are okay. You can have 0 and negatives under an odd radical. And then the third one is logs. Log of x, we know that x has to be positive. You can only take logs of positive values. So unless it's a piecewise where it's explicitly defined not to exist, if something passes those three hurdles, clears those three hurdles, you're never going to divide by 0. You're never going to be taking an even root of a negative number, and you're never going to be taking a log of 0 or negatives. Then guess what? The domain has to be reduced to all real numbers. And therefore, the function's continuous over that same interval set. So let's look at this one here. I have sine of x squared. Are we ever dividing by 0? Do you everyone see division by 0 there? No. Okay. No, we're good because sine is continuous everywhere. It's not like we're going to get a vertical asymptote, right? Like tangent. If that were a tangent, we'd have to be careful because now we could get division by 0. Tangent's undefined at odd pi halves. But sine is continuous everywhere. There's no radicals there, and there's no logs. So guess what? The domain is all real numbers. So now you could say h is continuous for all x in the set of real numbers. That's the quickest way to write it. The domain of h is all real numbers. Therefore, h is continuous over its domain. If you want to write them like that way, you can. But if you don't even talk about the domain, you can just say h is continuous for all real numbers. So even though we don't know what that graph looks like per se, we know that we can pick any two x values in the whole wide world and know that that function will be continuous on the closed interval between them. Okay. This one over here, it's another composed function. Cosine of x plus 1 is continuous for all real numbers. That's the inside function. The natural log of x on the outside is not continuous for all real numbers, but it is continuous over its domain, which is for everything greater than 0. So if I can find the domain of this function, I know that this composition of these two functions will also be continuous over that interval. Well, cosine of x plus 1, that domain is all real numbers, right? So we clear the hurdle there. But here's the deal. The outputs now of cosine of x plus 1 matter because we can only take logs of what types of numbers? Positive, that's it. I can't take the log of a negative number, and I can't take the log of 0 even. So is cosine of x plus 1 always positive? Or is it ever 0 or negative? That's the question. It might be. I don't know. Let's sketch a graph, shall we? Yes. This is where your transformations come in handy. If I look at the graph of this function here, I'm going to go ahead and sketch chala in one line. That's what the parent function is, chala. So it goes to 1 and to -1, and then it looks like this. All right, I'll do it as a dotted line. What does the +1 do to any graph, including this one? Shifts it up 1, right? So now it's the low points are going to be here, and then this goes up to 2. And now your sinusoidal axis is there. So now it's going to look like this. So is cosine of x plus 1 ever negative? No, it's never negative. So we don't have to worry about that. But is it ever 0? Yes, because we shifted up 1, we're going to have lots of, every time it bounces on the x-axis, we have another 0. So there's going to be infinitely many values that don't work. How do we list infinitely many values? We don't really. All we do is, if we can figure out how often they occur, if there's a pattern to it, we can just list 1 and say how often they occur. So let's go ahead and see if we can remember where this first positive x-intercept is. It's at x equals what? Pi, right? Because it's at a half cycle. It starts high, and that's where it hits the low point, and then it finishes high. So that's a half cycle, it's pi. And then how far apart are all the other ones? 2 pi. Once they're at the next low point. So x equals pi, And we could say plus 2 pi n. That's multiples of 2 pi. Now, we do have to do this. The default number group this year, remember, is real numbers. We don't want n to be a real number, right? We want it to be complete, entire multiples of 2 pi. So n has to be what type of number? If we say whole number, that works, right? 0 would be pi, 1 would be 3 pi. But we also want to, instead of doing plus or minus, if I just put plus and say n has to be an integer, that's the super bar z. N is an element of z, the integers. Now I can include -1 for n. And when n is -1, now I'm subtracting 2 pi. When n is -2, I'm subtracting 4 pi. So that's a real quick way to do it. You could say plus or minus as well if you want, just to be thorough. But you wouldn't need the minus if you let n be an integer. So now, since we let's just say this, we could say then that h is continuous for all x not equal to pi plus 2 pi n, comma, where n is an integers. Again, I have no idea what the graph of the natural log of the quantity cosine x plus 1 looks like. But I do know that it's continuous on those intervals. Okay? There you go. So if you include any closed interval that are not those as endpoints, it's gonna work, as long as it doesn't span another one of those in between those open intervals. Okay? All right, so continuity is an important thing on an interval. We can't do infinitely many tests on an interval, so we use the Pieper method. But if we recognize functions, we can now analyze domains of their compositions, which is what we did both times here. But they could be multiplied, added, subtracted as well. All right, that gives us time here before lunch to introduce your first big theorem, the intermediate value theorem. And I forgot to wear the shirt today. And you even reminded me about it. I'll have to wear it tomorrow. It was college day, so every Wednesday's college day, so we're supposed to wear a college shirt. Alabama, there you go. So here we go. The intermediate value theorem, also abbreviated IVT, which you don't even need the decimals. IVT, stylized without the I dot V dot T dot, just IVT. Short for the intermediate value theorem, okay? So let's look at the title. The, definite article, right? The, it's not a, it's the. I mean, or an, intermediate. It's the, definite article, it's the real deal. Intermediate, that means like not so hard, right? It's an intermediate level class. Well, intermediate doesn't mean not hard in this case. It means in between, in between. And then when we talk about value, it's Y value specifically. And when we talk about theorem, we're talking about the law. It's not just a good idea, it's the law. So this is called the in-between Y value law, right? Or the IVT for short. Now, anytime you have a theorem with a special name, like squeeze theorem, sandwich theorem, or the IVT, intermediate value theorem, you have to know what the theorem says. You should be able to reproduce the if and the then part, as well as use it, as well as formulating arguments based upon it, okay? So let's go ahead and read it. It says here, if, this is called the hypothesis. The if part is the hypothesis. If some function y equals f of x is continuous on a closed interval. That's it. That's all we need. Take a function, continuous on a closed interval. Then, the conclusion is the then part, then this is going to be guaranteed. Guaranteed, 100% of the time. Then f of x will take on every, again, if you want to put y value between f of a and f of b. F of a is just the function value at the left endpoint. F of b is the function value at the right endpoint. Then the function will take on every y value, essentially, between the y values of the endpoints. Put differently, if you pick a specific y value between the y value of the endpoints, call it y equals u, just some random y value that falls between the y values of the endpoints, then the theorem not only says that for sure that you're going to have that y value, but additionally, there's going to be at least one value of x on the x interval from A to B that produces it. Okay? Wow, that's amazing. Here's a graph of essentially what it says. I have the little blue graph right there. Okay? Is the blue graph continuous on the closed interval from A to B? Yeah. On the open interval with the peepers, no jumps, no holes, no vertical asymptotes. And you can see that the bridges are tied to the roads at the two endpoints. So the IVT applies. Okay. The y value of the left endpoint is f of A. The y value of the right endpoint is f of B. And in this case, I drew f of A below f of B. It could easily be switched around, right? If you draw horizontal lines between f of A and f of B and shade all the y values in between, the theorem basically says then there's no way to draw the graph from one endpoint to the other endpoint coordinate without lifting your pen or pencil. It's got to be continuous without passing through every y value in the shaded region at least once. Does that make sense? Yeah, it's kind of like a no-duh theorem, right? If I have to draw from this bottom left blue dot to the top right blue dot in any fashion without, it has to be a function, vertical line test has to be preserved, and I'm not allowed to lift my pen or pencil, can I do it without passing through every y value in here at least once? There's no way it can be done. Not through a continuum. Now, might you pass through certain y values more than once? Yeah, like look at this here. Draw a line right here. I pass on the way up, I pass on the way down. So you could pass through more than once, but you have to pass through it at least once. Is the graph guaranteed to stay in between those y values? No, you can see this one dips out. We don't know if it does or not. If all I know is it's continuous on the closed interval, and I know the y values at the endpoints, I really don't know much about what happens in between. I don't know where it goes, but I do know it has to pass through all the y values from low to high. When you flip it on your head, pick a random y value like y equals u. That's between them. Not only will that y value exist, but now, wherever it intersects with the graph, now the theorem also guarantees an x value on the closed interval. Could be an endpoint. This one's not. It also guarantees at least one x value that would produce it. Okay? So it's kind of like a no-duh theorem. So as you go into lunch, here's the easy way that I kind of have you remember it. Yeah. Why did the chicken cross the road? You've heard that joke. He had to, because chickens cannot teleport. Have a good lunch.